Okay, starting part C of this particular lecture, we can do a few examples involving quantum numbers that were given in the textbook. These are the ones that were not worked out for you, so I'll show you how to address them. One example would be, say, identifying the subshell, or in other words, the type of orbital along with the principal energy level in which the following quantum numbers would be found. So if n equals 3 and L equals 1, n equals 3 means principal energy level 3, so you just write a 3. L equals 1, as we saw up here, is a p-type orbital. So that would be a 3p orbital. We don't know which one because we weren't given the m sub L information, but we know that it's one of the 3p orbitals. If n equals 5 and L equals 3, well, we know that that's the fifth principal energy level, so we'd write a 5. L equals 3 is an F-type orbital. So this would be, this electron would be in one of the F-type orbitals in energy level number 5, or one of the 5F orbitals. And if n equals 2 and L equals 0, then we're talking about an orbital in the second principal energy level, and the type of orbital would be S, because L equals 0 is another way of saying S-type orbital. So 2S would be the type of orbital. If a shell contains a maximum of 32 electrons, what is the shell number? Or in other words, what is the principal quantum number? Well, something I haven't mentioned up to this point is that you can calculate the maximum number of electrons in a given shell as 2 times n squared. So you take the n, the principal quantum number, or the principal energy level number, and square it, and then multiply by 2. In this case, we're going about it kind of the other way around. Well, actually, before I do that, let me just say I've worked it out for the first 5 shells, or the first 5 values for n. And for 1, 2, 3, 4, 5, if it's shell number 1, then the maximum number of electrons is 2, because 1 squared is 1 times 2 gives you 2. For shell number 2, the maximum number of electrons is 8, because 2 is n, so 2 squared is 4 times 2 is 8. If it's shell number 3, the limit on electrons is 18, because 3 squared is 9 times 2 is 18. If it's the fourth shell you're talking about, then the limit is 32, because 4 squared, 4 times 4 is 16, times 2 is 32. If it's the fifth shell you're talking about, the maximum number of electrons is 50, because n is 5, so 5 times 5 is 25, times 2 is 50, and so on and so on and so on. We haven't quite gotten to it yet, but in practice, if the shell number, whatever the number of the shell happens to be, if it's the last shell that has any electrons in it, in the atom, then you'd normally be limited to 8 electrons for the outermost shell. So even if, say, the outermost shell is shell number 4, 32 is the limit on electrons in the fourth shell if the fourth shell is not the last or outermost shell. If the fourth shell is the outermost shell, then the normal limit would be 8. And if the outermost shell is the fifth shell, then instead of 50 electrons, you could only have 8, and so on. But we'll get to that later, so I'll remind you then. Doing the actual problem, the maximum number of electrons in a given shell is 32. So that means, in other words, 2n squared equals 32. Well, first thing you'd want to do is divide 32 by 2, and that gives you 16. So n squared is 16. So n is the square root of 16, which is 4. So n equals 4, as we actually already saw over here. And let's see, how many orbitals have L equals 2 and n equals 3? Well, actually, if you want to know how many individual orbitals there are, it's L that's really important. And because L equals 2 means that you're dealing with d-type orbitals And it doesn't really matter what n is. If you're dealing with d-type orbitals, then there are 5 of them. And they're all equal in energy, or they're degenerate. And each of them can hold a maximum of 2 electrons. So for n equals 3 and L equals 2, you could have a maximum of 10 electrons. But they were actually asking how many orbitals there are. So that would be 5, which would correspond to 10 electrons maximum. Okay. Okay. Section 6.4 is about electronic structure of atoms, or in other words, electron configurations. That is, where are the electrons within the atom? Okay, how many of them are there in the first principal energy level, and what types of orbitals are they in? How many of them are there in the second principal energy level, and what types of orbitals are they in? And so on until you've basically run out of electrons. We want to account for where all of the electrons in the atom are. And so the electron configuration is just an arrangement of electron, or is an arrangement of the principal energy levels, each of which is followed by the letter symbolizing the types of orbitals involved, and also indicating the number of electrons in that type of orbital in that principal energy level. We want to know this because the arrangement of electrons has a big effect on things like reactivity, because forming bonds is all about sharing or exchanging electrons. So it stands to reason that how many electrons you have and where they are would have an effect on how many bonds you form, how many bonds, that is, how many bonds can an atom of an element form with other elements, what types of bonds are formed, are they ionic or covalent, and that kind of thing. Especially when we're talking about bonding, we're concerned about the electrons in the outermost shell, which is also known as the valence shell of electrons, or the highest energy principal energy level. And that's because these electrons are on the outside of the atom, and they're the ones that other atoms will encounter first. And in fact, in most cases, those are the only electrons that any other atom will encounter, because they're right there on the outside. So these are the ones that are involved in bond formation. But in order to find out how many electrons there are in the outermost shell and what types of orbitals they're in, we have to find out where all the other electrons are first. Because when we map out the electron configurations, that is where we list out where the electrons are, we start with the lowest energy positions available, which would be in principal energy level 1, that is shell number 1, right down by the nucleus. And then we work out from there. And so it's only by starting at the very beginning down by the nucleus that you can work out how many electrons are left when you get to the outermost shell. And so it's important to be able to do the whole thing, not just, the outermost shell. The energies of the orbitals increase as n increases. We saw that diagram a couple sheets back in the last segment of the video, where as n goes up, the energies go up. It's not linear, remember. There's a big gap between n equals 1 and n equals 2, and then smaller gaps between n equals 2, and then a very much smaller gap between 2 and 3, and so on. But they do go up as n goes up. The energies of electrons within a given shell, or within a given principal energy level, will go up according to S, P, D, and then F. So within a given shell, that is within a given value for n, the f orbitals will be higher than the d in energy, d orbitals will be higher energy than p orbitals will be higher energy than s. Okay. There are some anomalies. You would, like we saw in the chart or the diagram a few minutes ago, you would expect 4s orbitals to be higher in energy than 3d. But in fact, it's the other way around. 3d is greater than energy than 4s. And that has to do with complicated concepts like shielding of outer electrons by electrons that are closer to the nucleus. There's an attraction between the positively charged nucleus and the negatively charged electrons, but the level of attraction between the electrons and the nucleus can affect the energy of the electrons, and that attraction can be affected by the however many electrons there are between a given electron and the nucleus. And that's kind of what shielding is about. But we'll get to that in a little more detail later. As you go left to right in the periodic table, so here to 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 here, and so on. Each time you go from one space left to right, you're adding, well, you're going up by 1 in terms of atomic number, and that means you're adding 1 proton in the nucleus, and you're also adding 1 electron to the cloud of electrons around the nucleus. Okay, so you're adding 1 proton and 1 electron. Electrons generally want to be in the lowest energy position available, and that's because nature generally favors lower energy or greater stability. So if there's a low energy position available, an electron will go for it until that position is filled, and then the next electron in will have to go for the next lowest energy position that's available, and so on and so on and so on. So when you try to find the electron configuration of an atom, in other words, listing out where the electrons are in terms of energy level and orbital type, you basically just write it as a list of orbital types in each principal energy level with the number of electrons in each type of orbital written after the orbital letter as a superscript. And I'll show you numerous examples of that later, so don't worry if that doesn't make sense. So what we normally do is we take the total number of electrons in an atom, which is normally just the atomic number, and we build up an electron configuration by taking those electrons one by one and placing them in the lowest energy position available. So the first electron would go into the s orbital in n equals 1. The second electron goes into the s orbital of n equals 1. But at that point, the s orbital in n equals 1 is filled. And so is n equals 1, because the s orbital is the only type of orbital allowed in n equals 1. So then if you have a third electron, that has to go into the s orbital of n equals 2, as does the fourth electron. But now the s orbital of n equals 2 is filled, but n equals 2 can also have p type orbitals. So the fifth electron would go into one of the p type orbitals in n equals 2. And so on and so on and so on until you run out of electrons. And that's how you build up an electron configuration according to what's known as the Aufbau Principle. The Aufbau Principle, is, well, the word Aufbau is German, and it just literally means building up. Sometimes some books actually call it the building up principle. So because you're building up an electron configuration, essentially from the ground up, from the lowest energy possible position, up and up and up until you run out of electrons. And that is the Aufbau principle. The form of the electron configuration includes the number of the principal energy level, that is the shell number, the letter designation of the orbital type, and the total number of electrons in that type of orbital in that shell, written as a superscript. So as I was saying a moment ago, if you have an atom with 1 electron in it, hydrogen in other words, because that's atomic number 1, that would have an electron configuration that's written as 1s with a superscript 1. And you would say it as 1s1. The big 1 at the beginning means n equals 1, the first principal energy level. The s indicates that the electron is in the s-type orbital of n equals 1, which is a little redundant because that's the only type of orbital that's allowed in n equals 1. And the superscript 1 means that there's one electron in the s orbital of n equals 1. So that is the electron configuration for hydrogen. For helium, you atomic number is 2, and you have 2 electrons. Well, the second electron actually goes into the same orbital as the first one because the s-type orbital in n equals 1 can hold 2 electrons maximum. So the electron configuration for helium is 1s2. That is 2 electrons in the s orbital of shell number 1. At this point, the s orbital in shell number 1 is full. And so if you want to do the configuration for lithium, which has an atomic number of 3 and therefore has 3 electrons, you have to go up to n equals 2 to accommodate that third electron. So lithium has an electron configuration of 1s2, meaning that the s orbital in n equals 1 is full, and the third electron goes up to the s orbital in n equals 2. And the superscript means that there's only one electron in that orbital. And you go on like that. And we'll show some examples in a few minutes of actually doing that. As I said, there are some anomalies in the energies of orbitals where they're sort of, particularly the first one that we encounter is the relationship between 3D orbitals and 4s orbitals. You would expect 3D orbitals to have less energy than 4s orbitals, but in fact, it's the other way around. 4s has less energy than 3D. What that means is, according to the rules of the Aufbau Principle, since electrons will go into the lowest energy positions available first, that means that 4s that is the 4s orbital will fill before any of the 3D orbitals fill. So that's the practical consequence of that little anomaly in their energies. And so it can be a little confusing in remembering the order in which orbitals fill because of these anomalies. Most of them fill in the order that you would expect them to, but not all of them. By sheer stroke of luck, it's actually quite easy to write out a little diagram that will show you the correct order in which electrons will fill in orbitals as you're doing an electron configuration. And this figure is shown in the book, but it's also really easy to make your own. All you have to do is write out the types of orbitals in columns, and in the rows, you would have the principal energy levels. So you make a column of all the s orbitals for 1s, 2s, 3s, 4s, 5s, 6s, 7s. And then next to them, you write out all the p orbitals. The thing to remember, though, is that there are no p-type orbitals in n equals 1. The p-type orbitals start with n equals 2. So you'd write 2p right next to 2s, and then 3p right next to 3s, and 4p and 5p and 6p and 7, and so on. Then you do the same with the d orbitals, but remember the d orbitals don't start until n equals 3. So you write 3d right next to 3p, and then 4d next to 4p, and 5d and 6d and 7d. Then you do the same with the f orbitals, but again, remembering that the f orbitals don't start until n equals 4. So you'd write 4f right next to 4d, and then 5f, 6f, 7f. And then you just draw diagonal arrows through the list. So the first arrow goes through 1s because the 1s orbital, that is the s orbital in n equals 1, is the first orbital to fill. And then you go to the top of the next arrow, and that goes through 2s because the s orbital in n equals 2 is the second one to fill. Then you go to the top, then you're done, no more orbitals are encountered on this arrow. Then you go to the top of the third arrow. Next, you hit 2p, because the p orbitals in n equals 2 will be the next ones to fill. And as you go along the arrow, then you come to 3s, because the next ones to fill after 2p would be the s orbitals in n equals 3. Then you're at the end of that arrow, so go back to the top of the next arrow. Then we come to 3p, because right after 3s orbitals fill, the 3p type orbitals start filling. And look what the next one is, 4s. You would have expected 3d to fill next, but according to this list, it's 4s, and that's right. That's actually correct. 4s orbitals will fill next, and then you go to the top of the next arrow, then you get to the 3d, and then 4p, and then 5s, and so on. And if you follow these arrows, you will get the orbitals filling in the correct order. I basically made a practice of reproducing this little table on all of the tests and quizzes when I needed to take them. You've got the one in the book you can use. So I would, certainly recommend having that handy whenever you're doing anything involving electron configurations. Now, the one thing you still do have to remember is how many electrons maximum each of these types of orbitals can accommodate. Okay, So S-type orbitals, there's only one orbital of the S-type in each shell. So that means in S orbitals, in any the S orbital in any given principal energy level can only hold a maximum of 2 electrons. For p-type orbitals, though, there are 3 of those with a maximum of 2 electrons each. So that would be a maximum of 6 electrons for the p-type orbitals in any given shell. So when you get to the 2p orbitals, the first electron that goes into them would be 2p1, and then 2, 3, 4, 5, until you get to 2p6, and only then is the p orbitals in n equals 2 filled, and only then can you go on to 3s. For the d-type orbitals, there are 5 individual orbitals of the d-type in each principal energy level that has them. And that means a maximum of 10 electrons for the d orbitals in any given shell. And for the f orbitals, remember there are 7 of them of different orientations in any given shell that has f orbitals. And that would be a maximum of 14 electrons in the f orbitals. Okay. When you're doing electron configurations, it turns out that the last orbital into which an electron will go, that is basically the orbital that you're putting electrons into when you run out of electrons, is predictable based on where the element is in the periodic table. I've divided up the periodic table here into sections, and the sections are actually named after the orbital that gets the last electron when you're doing an electron configuration. So the first 2 columns over on the left are known as the S block, because the last electron in to these elements when you're doing an electron configuration will be in an s orbital of whichever principal energy level corresponds to the number of the period that the element is found in. So for instance, if you take potassium, which is in period number 4, that means the last electron into potassium will be a 4s electron, because it's in the s block and it's in period number 4. So 4 is the number of the outermost shell of electrons, or the maximum principal quantum number. And since it's in the s block, you know that the last electron in will be an s-type electron. And since potassium is the first element in the s block for period number 4, you can tell that there will be one electron in the s orbital of n equals 4. So basically, the electron configuration for potassium ends in 4s1. You can tell that just by where it is in the periodic table. There are 2 elements in each row of the s block because the s orbitals can accommodate 2 electrons. All right, so potassium ends up with 1 electron in the s orbital of n equals 4. Calcium ends up with 2 electrons in the s orbital of n equals 4. So the electron configuration for calcium ends in 4s2. Okay. The 6 groups over on the right-hand side, that is the taller groups over on the right-hand side, the nonmetals, and are part of what's known as the p block, because the last electron into the electron configuration for any element in the p block will be a p-type, will go into a p-type orbital in whichever principal energy level corresponds to the period number over here. So that's what we mean by NP. And there are 6 of them because there are 3 p-type orbitals in each shell that has p orbitals. And the p orbitals can accommodate 2 electrons each, but there are 3 of them. So that's a total of 6 electrons that can be accommodated in the p orbitals of any given principal energy level. And that's why the first element here, say boron, is in period number 2, and it's in the p block, and it's the first element in the p block. So this means that the electron configuration for boron ends in 2p1 because it's the first element in the p block. Carbon is in second period in the p block, and it's the second element in the p block from the left, which means that the electron configuration for carbon ends in 2p2. And then nitrogen ends in 2p3, oxygen ends in 2p4, fluorine ends in 2p5, and neon ends in 2p6. And at that point, the p orbitals in n equals 2 will be full. And if you add 1 more electron, that goes into the s orbital of n equals 3. So the configuration for sodium ends in 3s1. And so on and so on and so on. Okay, so that's for the main group elements. Transition elements will fill the, basically they fill the s orbitals for n, which would be whatever the period number for the element is. And then they fill the p orbitals for n, and then they start filling the d orbitals of the last shell down. So n equals n minus 1 d. The transition elements are also known as the d block elements. And you'll notice if you count across, there are 10 spaces in the transition elements, or the d block, because there are 5 d orbitals for any shell that has d orbitals, and they can each accommodate 2 electrons for a total of 10 possible electrons in the d orbitals of the valence shell. So D1, D2, D3, D4, and so on. If we're talking about something like scandium, the last electron into scandium will be a p electron in the shell n minus 1, n here being 4, the period number. So the last electron in scandium would be a 3d electron for 1 less than the period number. And scandium is the first element in the d block, so the scandium electron configuration would end in 3d1. Titanium would end in 3d2. Vanadium would end in 3d3. Chromium would end in 3d4. Manganese would end in 3d5. Iron would end in 3d6, and 3d7, 3d8, 3d9, until zinc, which ends in 3d10, because it's the 10th element across the d block. And it's the same idea with the elements down at the bottom. They're known as the F block because the last electron into the electron configuration for the elements down there will be an F electron in the principal energy level that corresponds to the period number -2. Okay, so the last electron into the electron configuration for cerium will be an F electron in the principal energy level 6 - 2, which is 4. So 4F1, 4F2, 4F3, 4F4, 4F5, and so on, up until you get to 4F14 for lutetium. And notice there are 14 elements in the F block because you're filling the F orbitals here, and there are 14 spaces available for electrons in the F orbitals. There are 7 types of F orbitals in any given shell that has F orbitals with a maximum of 2 electrons each. That's 14 electrons for the F orbitals in any given shell. And that's why there are 14 spaces going across in the F block. Okay, looking at specific electron configurations is what we'll start on next time, but we're over on time on this lecture also, so I'm sorry about that. But we'll pick up with electron configurations and orbital diagrams next time.